Let's see. Today, I'm gonna talk some more about exploratory stuff that you can do with our data. We, in the recorded lecture from Friday, talked about cluster analysis. I will talk some more about that either today or Wednesday if we have time. But I also today wanted to talk about principal component analysis. That's one thing you're going to do on your homework, and a related technique called singular value decomposition. So I'll show you how you can use these two techniques to make pictures and compute numbers that tell you about, in a big multivariate data set like the ones that we're working with, tell you about structure that there is in the data. I'll talk more about it. These are very valuable exploratory techniques. They take a little practice to understand what they're doing and how to interpret the results. But if you can get comfortable with using them, they're one of the first 2 or 3 things that I would recommend doing when you have data like this, a multivariate data set. Because if you just have a handful of numbers that you do from some experiment, you can just draw a histogram or a box plot, you can compute an average and a standard deviation, and you know a lot about the data. But if you have a big data set like ours, thousands of features and dozens of samples, you can't easily look at it, summarize it, pick it up and look at it. So techniques that come from multivariate statistics are useful for that purpose. Visualizing, summarizing, boiling down to summary stories a large data set. All right. So to get us started with this, I'll give you some background, and you don't have to perfectly get all of this background in order to be able to use principal components, say. But this will explain, in detail what you are doing. So you might want to reference the recording that we're going to have from this lecture again, and review what we're about to say. Okay, because principal components, for example, a lot of people use them. You have probably seen them in a presentation or a paper. They're easy to do. It's easy to click a button to do principal components or write a command to do it. It's not easy to explain what it is. So bear with me here. Let's just do a little bit of talking about what principal components is. So we have, let's say we have a data set X, which is M by N, M features, N individuals or samples. That's multivariate data in a sense. Usually in classical statistics, we have N observations on a single response variable. And we do regression or ANOVA or t-tests and stuff. But now we have multiple variables. We have lots of variables. Each variable corresponds to one feature, maybe a gene. So suppose we boil this down to a covariance matrix. Let me tell you what a covariance matrix is. We are going to try to summarize the structural components of this collection of numbers. What I mean by that is, suppose these M times N numbers in this big matrix were completely independent of each other, there's no interrelationships between the features or between the samples. If I just randomly generated M times N numbers from, say, the standard normal distribution, there wouldn't be any structure to the data. This number has nothing to do with that number or any of the other ones. They're just randomly bobbing around. As opposed to maybe a time course study, where across the columns we have temporal measurements over time in response to exposure to something. I expect there to be structure now, because as you go across the columns, you're following a time course. So I would like, for an exploratory technique applied to these types of data, to be able to tell me, is it the first category or is it the second category? Is there any structure? And if there is, can you give me some insight into what it looks like? What relationships are there under these data that are not just completely random and chance-based? So here's what we're going to do. Let's compute, or let's think about a something I'll call capital S, and it's going to be n by n, and it's called a covariance matrix. So S, if I were to write it out, would have in the first row, first column, what we could call S11. This pen is not doing what I want it to. The first row, first column, we could call it S11, as in first row, first column. And that is the sample variance for the first column in our data set. In columns, each column is, say, a person, or a rabbit, or a mouse. If you were to take the first column, you have m numbers, just compute the sample variance of those numbers and put it right there. Here is the sample variance for the second sample, ... Here is the sample variance for the nth individual or column. In the first row, second column, we'll call it S12. That's the sample covariance between the first and the second individuals. A covariance, think correlation. It's an unscaled correlation. Correlation has to live between -1 and 1. Closer you are to +1, the tighter the positive relationship, linear relationship between the two variables. Closer you are to -1, the tighter the negative linear relationship between two variables. Closer to 0, no linear relationship between the two variables. That's correlation. A covariance is basically that, except it's not restricted to -1 to 1. It can be -infinity to infinity, but it's still the same interpretation. The bigger positive, stronger the positive linear association. The bigger negative, stronger the negative linear association. Closer to 0, no linear association. This S12 would be the covariance between individual 1 and individual 2. So take column 1 and column 2, like over here in R. Let's make up some data real quick. X is completely random data, no structure whatsoever. I'm just going to make a matrix, and let's do 1,000 features and 10 samples. So I'm going to do 1,000 rows, 10 samples, like that. So there's an omics data set, and there is 0 structure to the data, completely randomly generated. I could compute the variance of the first individual, sample variance, 0.97. I could compute the variance of the second individual. I could compute the correlation between the first and the second individual. So if we plotted x1 versus x2, looks like that. There is no correlation because they were generated that way. It's just completely circular, random scatter. Correlation would be fit the best fitting line to that and give me a scaled version of the slope, basically. Are they really tightly following each other, or are they just spread out like this? So in this case, the correlation, I could compute it. The easiest way to compute the correlations is to use the core function. So if I say core x, what I get is a 10 by 10 matrix. Let's round that so it's a little easier to see. Just like that. 10 by 10 matrix, still kind of hard to see. Why is there that much? Oh, core X. This is a correlation matrix. First row, second column. That is the correlation between column 1 and column 2. Very close to 0. You can see from the picture they're not correlated. So the covariance is an unscaled version of this minus 0.02. We don't have to be able to, I don't care that you know the formula for what the covariance is. But it's an unscaled version of this. It could be minus infinity to infinity. It's going to be close to 0 because the correlation is close to 0. So let me go back to the things we computed up here. The variance of the first column, the variance of the second column, and now let's look at what happens if I do variance of x. We'll round that to 2 digits so we can see things. This is what I called capital S on the whiteboard. First row, first column is the sample variance of the first individual. Second row, second column is the sample variance of the second individual. And this is the covariance between individual 1 and individual 2. It's actually the same as the correlation, but that won't generally be the case. Only for this individual. So that we have M, in this case, 1,000 features and 10 individuals. What I could do is look, if I wanted to look at structure between the individuals, I could compute this thing. This is a specific to individual variation. So across all the features, the sample variance for mouse 1 is 0.97. And across all those 1,000 features for mouse 2, it's 0.98. Across all the features, the covariance is that. I could have done, instead of a n by n covariance matrix that's specific to the individuals, I could have gotten an m by m covariance matrix that would be specific to the features. In which case these would be variances of the features, like row variances, and the off-diagonals would be covariances between features. Both of those are interesting things to look at. What structure is there in my data in terms of how the individuals relate to each other? Can I see, for example, that treatment individuals differ from control individuals, structurally, big picture-wise? And can I see that some of the genes or markers or whatever differ from other markers systematically? This principal component stuff can go either direction. The direction I'm showing you right now is I'm looking at structure among the columns, among the individuals. So I start with a 10 by 10 or n by n matrix of covariances, or I could start with the correlations. Either way, let's start with the covariances right now. This 10 by 10 matrix. This 10 by 10 matrix kind of, if you think about it, you can think about it like it contains the information about total variability among your data. Our m by n matrix, it's not all just one number repeated that many times. It's lots of different numbers. There's variation. Some of that variation is individual 1 differing across its features. Some of it is individual 10 differing across its features. Some of it is feature 2 differing across the individuals. There's just different angles from which there's variance, there's variability. And here's all the variance information, individual variances and all the covariances. So we're going to look at this matrix 10 by 10 as kind of a representation of the total information in my data set. And we're going to ask, what can I say about the structural components of this thing? A 10 by 10 symmetric matrix. If you've had linear algebra, it's also, if we're dealing with a covariance matrix, it's a positive definite symmetric matrix. And I'm just curious, anybody who has had linear algebra, if you wanted to summarize a symmetric positive definite matrix in terms of component pieces, what does that bring to mind? Any specific linear algebra concept for you? I'm just curious. You don't have to know this, but if you have a symmetric matrix like we do, and you want to break it up like a puzzle into its core puzzle pieces, these are the main pieces that when you put them back together, you can reproduce this, but these are simpler sub-pieces of this big thing. Anybody know a magic word? Anybody know eigenvectors, eigenvalues? The magic word is eigenvector and eigenvalue. Let me tell you a little bit about what those are. You don't have to be a linear algebra expert to understand and use these things. We have this covariance matrix. It's the total collection, it's the total information that's in my data set. It turns out, let me finish this here. So this is S1n, Sn minus 1n. This is a symmetric matrix, which means that you can reflect it across the diagonal and it's the exact same thing. Okay, so if you can take a matrix like ours and find a vector E and a scalar, like a number, not a vector, not a matrix, but a number, lambda, such that that holds, then lambda is called an eigenvalue of S, and E is called an eigenvector of S. This is a mathematical concept, so it's kind of abstract, but it's an important concept, especially for multivariate statistical analysis. What is this doing? In a sense, we're simplifying capital S. We're taking this n by n matrix that contains all this variation information. There's S. We're going to multiply it by some vector E. So S is n by n. E needs to be n by 1 if it's a vector. It's not a matrix, it's just a vector. So in order for the dimensions to match up right, E needs to be n by 1. Lambda is just a scalar, so I'll just write it like 1 by 1, just a single number. And E, again, is n by 1. So I have taken, there's some vector E such that I can replace this S, which is an n by n matrix, with a scalar. I can boil an entire matrix down to a scalar if I write it this way. And what it ends up being is like a puzzle piece. If you have a puzzle and it's a complicated picture, but there's, say, 5 puzzle pieces that pull this out. This is a core piece of the puzzle. And here's the other core piece, here's another one, here's another one. If you put them all back together, you have the exact same picture back. But this relationship, if I can solve this relationship and find, here's a lambda and a corresponding E, that if you put them together, you can do this. You can re-express S this way. Here's what you get to say. E and lambda. Okay. E, what we're going to do with principal components, we have, in this case, we're going to say we have n individuals. Can we boil those n individuals, think of them as variables for a moment, can we boil those variables down to a smaller number of new variables that we make up, and make those variables up in such a way that they are most informative. And let me tell you what I mean by that. We are going to try to take linear combinations of the individuals, or the variables as we're considering them right now. So let's say x, we're going to write it like x1, x2, xn. So this x1 is m by 1, and this is m by 1, and this is m by 1. All I did was rewrite x. It's m by n. So x1, all that is the numbers for mouse number 1. It's like the microarray or the whatever device for mouse number 1. x2 is mouse number 2, ... xn is mouse number n. Okay, so let's consider variables like, let's call it y, that are linear combinations of these n variables. So I'm going to do a1, some constant, times x1, plus a2 times x2 plus ... an times xn. Those are linear combinations of the original variables. One kind of simple way to take the original variables and boil them down to a single number. If I did that, you tell me what a1, a2, ... an is, then I can take my x, m by n matrix, and replace all those n columns with just a single column. I've taken my n individuals, my n variables, and I have boiled them down to a single number. Suppose we wanted to do that. We haven't said anything about what a1, a2, ... an is. But suppose we're looking for variables like this, that type, and we want to find, by the way, notice that I could write this as a transpose x if a is a vector. It's an inner product of a with x. Can we find a, those coefficients, such that even though I boiled those n variables down to just one, can I find a way to do that such that I keep as much information about the total data as possible? If this n by n matrix is like all the information we have, it's variances and covariances. It is how things differ. That's how we are different from just a matrix of one number repeated all the time. So if I wanted to boil those n variables down to just one, I could do that in an infinite number of ways. There's an infinite number of a's that we could choose. Go find the one value of a that maximizes the amount of variability explained. If you wanted to take a collection of, let's say, mice or people, and you wanted to, with one variable instead of n, you wanted to explain them, separate them, spread them out as much as possible. We're going to take everybody in the room, and there's 10 variables that I could dream up that we could measure for each person. What's your age, gender, race, IQ, all those things. And I'm going to boil that down to one number for every person. Instead of those 10, I'm going to boil it down to one. And I want to pick that one number so that I can spread you all out and say, okay, you're different from you in this way, because your number was this, your number was that. A bad choice would be, okay, everybody gets the number 10. Because now, line up by your number, you're all standing in the exact same place. There's no information in that particular variable. So if I want to boil it down to one number that spreads you out as much as possible, what summary statistic do I want to maximize? Let's find A, this way to collect those 10 variables that we could measure for everybody, and put them together, boil them down, do a linear combination, say, into one number. I want the most informative choice for A, so you fill in the blank, find A such that what is maximized? Do you think? Okay, mean is one choice. If you want, okay, so the bad choice was everybody's number 10. Line up on the wall according to your number. Everybody stands in one place. Can't tell anybody apart. If I want to tell you apart as much as possible, what do I want to maximize in terms of the number that I give you? The variance. I want the variance of this thing to be maximized. That's information. If there's high variance in the number, it's informative because I can spread you all out, as much as possible. I take those 10 variables, boil them down to one in such a way that the variance of A transpose X is maximized. For example, this is not a bioinformatics case, but it's a data set that I've been playing with. I have some data where the individuals are retired players from Major League Baseball. And for each of them, you have career playing statistics. You know whether they're in the Hall of Fame or not, by the way. The goal is to predict, is a player going to get into the Hall of Fame? And your variables are like career batting average, career hit total, RBIs, home runs, and all those things. A bunch of quantitative numerical variables. You can replace, let's say, the 6 main quantitative variables that I was playing with: hits, home runs, RBIs, batting average, slugging percentage, on-base percentage. You can boil those down to just one variable and still preserve like 80% of the total information that was in all those variables. You can turn all those variables into just one and not lose very much information. If, in that case, basically you average up the career statistics. Take hit total, multiply it by 1/6, add to RBI total, multiply by 1/6, add to home run total. Do that for all 6 variables, and that spreads it out as much as possible among all variables like this. And you can also say that amount of spread is 80% of the spread you would have had if you had kept all the variables. So you have reduced the dimensionality of the problem. You've taken a big, messy m by 6 matrix and turned it into one variable that you can now make a histogram with or a box plot with. So this A that we're talking about right here is called, it is the eigenvector of S. What's the solution? We just kind of outlined a problem. Boil your n variables down to just one, and do it in such a way that you maximize the variance of the resulting variable. The solution is that A1 is E1, the first eigenvector of capital S. And the variance of the resulting variable is lambda 1, the first eigenvalue that goes with that eigenvector. We can continue going, though. There would be the second task in principal components. So I am, have not mentioned this, but we're going to treat these things as having been normalized. Length, what's that? The A's don't have to be normalized as long as we define the E's to be normalized. So if E has been normalized, that means length 1. It's a unit length vector. You could do that. What's going to happen is in the software, you're going to ask for, give me the eigenvalues and eigenvectors for capital S, and it's going to give you back normalized. Any software is going to do that for you. It will do that for you. One last thing here before I show you step 2. This Y1, which is A transpose X, is called the first principal component. It is a new variable. We started out with our n variables. We just created a brand new one. It's called a principal component. Special new variable designed in a particular way. It's a linear combination of the original ones, and it maximizes, it has the maximum variance among all possible linear combinations of the original ones. That's the most informative way that you can combine the R variables in a linear combination. The next step is also useful because now we're going to say, okay, here's the single best one-dimensional way that I can spread out my data or explain my data. What's the next best way? Now we're going to find A2, and it turns out to be the second eigenvector with variance A2 transpose X, which is lambda 2, and Y2 is called the second principal component. I'm going to show you an example in a second in R. But let me finish writing just a line or two here, and then we'll go to R. This is the next best way to explain, and the piece that is important here is that A1 transpose A2 is equal to 0, which means that PC1, principal component 1, best single way to put our variables together in a linear combination to maximize variance. A2, second principal component, is uncorrelated with that first one. What's the next best way to spread these things out? In the Hall of Fame example, the best single way to spread the players out is to basically average their career stats. Kind of makes sense. Hank Aaron is very different from somebody who only played 1 year in the league because his stats are just off the charts. All of them are big positive numbers compared to the lower ranking people. You can spread them out as much as possible that way. The second principal component says kind of adjust for the fact that big career stats is number 1 in terms of spreading things out. What's the next best story or structure? And it turns out in that case to be interesting, not something you would have seen by just opening the Excel spreadsheet and scrolling through. Turns out that the second principal component says take, and we don't need to go into the details, but it says contrast variables that only the players that are enormous and hit tons of home runs, like Barry Bonds, will have big values for, and compare that to, contrast it with variables that players who are good players but don't hit lots of home runs have big values for. So you could kind of summarize that roughly by saying principal component 2 is highlighting differences between power hitters and small ball hitters, if you know a little bit about baseball. The point there is that by decomposing a covariance matrix into its component puzzle pieces, eigenvalues and eigenvectors. By doing that, we can reduce those variables, all of our variables, down to individual variables that are informative, most informative. And they go in distinct directions. Best way to spread them out is this. Now that you've seen that, I'm going to tell you a totally different direction to look. And among all of those directions, here's the best one in that direction. If you're familiar with multivariate normal, bivariate normal, you know, we have, if I have a single univariate data set and I draw a histogram, see a bell-shaped curve, I could say my data came from a normal distribution. Suppose I had two numbers, though, that I was going to measure. Instead of just your height would go down here. Instead of just your height, I'm going to measure your height and your weight. That's multivariate data. There's two variables that I'm measuring. I could have an extension of this bell-shaped curve in the multivariate case. Now it looks kind of like a surface like that. It's a bell-shaped kind of elliptical surface. Suppose we had data on height versus weight, and we drew a scatter plot. And maybe it looks like that or something. So that's like looking straight down. If you went over to this picture and looked straight down on it, if you just had points, you would just see those points. You don't see the actual 3D stuff. Here's another way to think about this eigenvector, eigenvalue stuff. There is an axis that describes the direction of maximal spread in these data. So they are varying. They're not all at one point, but they're not circular. They're kind of elliptical. And the direction of maximal of where most of the spread is that way. Most of the data is spread out. That's the biggest spread that way. It turns out that E1, the first eigenvector, is that direction. It tells you what direction do things spread the most. E2 is the direction that is perpendicular to E1, that is the next best direction. So another way to think about these principal components is you're taking the original axis, x-axis, y-axis, and the original data points, like these data points, and you're rotating them so that now they are oriented in this natural way. That instead of the x-axis, now we have this axis, and instead of the y-axis, now we have that axis. We rotated the orientation so that now if we kind of turn and look at it that way, here's the biggest spread, there's the next biggest spread, and so on. Okay. Eigenvalues, eigenvectors, admittedly abstract concept. If you've never had linear algebra, then probably went in one ear right out the other. The first time you've heard this, file away in the back of your head. Eigenvalues, eigenvectors are important. That's like the most important piece of linear algebra that you can take and apply to the real world data analysis, I claim. Look them up on Wikipedia and see if you can get any more intuition. Otherwise, follow along, and I will reuse the wording, here and there. But the main piece of this story is that we're going to start with a covariance matrix, all the variation, all the information in my data. And we're going to try to decompose that in a meaningful way. So enough words, let's go see it in action. I have loaded in the yeast data. And if you watched the lecture video from Friday, we did some exploration of these data. And up here, in kind of the preamble, we kept track of things like who ran. So the yeast data, just as a reminder, we have 23 arrays. Each array was prepared with a batch of yeast. And we have some number of thousands of features or genes on each of the arrays. We also have some, quote, metadata for the arrays, such as what was the strain of yeast that was used on array 12 and array 14 and so on. We have strain. We have the technician that prepared the array. There were two technicians. Actually, I guess there's, well, yeah, two distinct technicians. And only one of them has their name attached to each of these arrays. There were a few unknowns, so we didn't know which of the two it was. And we also have the year in which the array was prepared. So I have three kind of meta variables. What's the strain, who prepared the array, and what year was it prepared on. So where did I get back here? So we have, after we do the processing, read in the data from all those different individual files, and filter only the rows that are common to all the arrays, because some of these arrays came from different years and they aren't exactly the same. So only pull out the data for these arrays that showed up on all the arrays. That's what this code is doing here. And that leaves us with 6,740 genes. Then pull out only the variables that we're going to play with, which were the median intensities for the two channels. There were two channels. One of the channels is a control channel on each one of these arrays, which means that a control strain of yeast is in that channel on all the arrays. You can see that like up here in this in these comments. So for example, array 69973 has a fuel strain of yeast versus the control strain of yeast. It was prepared by Stambuk, and it was from 2006. And I have pulled out the columns of the original data that correspond to the median intensity by the two channels, Y1 and Y2. I log transformed them, and then I took the difference between the two. So these are kind of like adjusted intensities for each of the 23 arrays. They're adjusted for like a background intensity amount. That control array, that control channel on each of the arrays is kind of an internal standard. And one way to adjust for that internal standard is to subtract it off from all the other numbers. So we're going to treat capital Y as the data. 6,740 by 20. Right. So let's see what we can do. We have 4 minutes. Okay. Let's make a couple of pictures. I don't think I've made these in class yet, but just to get started, here's a box plot of Y1. And Y1 is channel 1. In channel 1 is the control strain of yeast on every array. So let's get the control channels and make side-by-side box plots. Just starting to kind of look at the data, get a feel for it. Side-by-side box plots. We have 20-something. How many arrays do we have? We have 20 arrays. So I have one box plot for each array. Here's the first array, and there's 6,740 numbers in channel 1. If channel 1 contains control strain of yeast, what would you expect these boxes to look like, ideally? Would you expect there to be a lot of differences from array to array? Not if it's the same stuff, which as far as we know it is. It's just the same strain of yeast. You know, they weren't like, it's not like a family that grew up in China versus a family that grew up in Kentucky or something. This is just yeast that they grew. I wouldn't expect big differences. So for example, array 13 is a little concerning. Array 13, and most of the numbers on array 13 are shifted down relative to their counterparts on the other arrays. And just generally, you can see a fair amount of variability from array to array. So that's just an indication that there can be substantial technical variation. We've talked about biological versus technical replication. Technical replication is usually aimed at trying to not have this kind of variability. It's the same yeast, it's just different arrays. I don't expect there to be systematic differences between the arrays in terms of the same yeast. So we might want to adjust these numbers so that they don't vary so much. Okay, so that's one picture, very simple picture you could make to start looking at the data. This picture, I'll just make it real quick and tell you what it is. This is means by strain. So of all the control strain arrays, go get their numbers, get all the numbers for the yeast or the fuel strain, for the baker's strain, and the wine strain. So roughly speaking, you see there are differences between the strains. In a global way, this is not feature by feature, this is like all across all the features. The fuel strain box is quite a bit higher than that for the control box, for example. So there is some structure in the data. There is differences between the strains, for sure. Let's look at differences between technicians. Wonder whether there are differences between technicians. That's the picture. Of all the arrays prepared by technician done, that's the box plot of all the numbers. Here's the box plot for Stambuk. So that's a little concerning as well, for reasons that I'll talk about in a minute, or probably next time. Suppose Stambuk did all the fuel arrays and Dunn did all the wine arrays. And we want to go searching for features that are different between, as compared to the control arrays. Does this picture say that the fuel arrays are more different than the wine arrays? The problem here is if it is that Stambuk did all the fuel arrays and Dunn did all the wine arrays, you have confounding, because you can't disentangle whether these differences are fuel versus wine or Stambuk versus Dunn. There's a confounding issue with these data because there are such big differences between the technicians. We're not done with these data. We will play with them some more. So I will fill those blanks in a little bit as we go. We're just about out of time, but let me just show you what I'm talking about with principal components real quick. So what I'm going to do is I'm going to compute the sample covariance matrix. So I'm going to do variance. If you do variance of a matrix, it will give you a covariance matrix with treating each of the columns of your original one as a variable. So here we have a 6,740 by 20 matrix. I'm going to do var of y, and I'm going to get a 20 by 20 matrix. And then what if we did PCA is principal components y. Print that out a couple of different ways. And then let me show you what it's doing behind the scenes. It's all it's doing, all principal components is doing is an eigen decomposition of a sample covariance matrix. So here we'll compute 10 by 10 covariance matrix. Looks like this. So all of these are sample variance of array 1, sample variance of array 2, sample covariance between array 1 and array 2. Principal components, you can do it with the prcomp function. And if I just type the output PCA, let's see, I get this. So I get, this is standard output from principal components. And one of the main things that it gave us is this PC1, PC2, and so on. These numbers in this column define A, that collection of constants that we're going to use to make a linear combination. So principal component 1 would be minus 0.077 times column 1 plus minus 0.23 times column 2 plus that times column 3 plus ... That's what the principal component is. It's a linear combination of the original variables. So that these numbers in the first column are these numbers, A1. It's the first collection of coefficients. That's what's in this output. I also did summary of the output, and it tells me something additional. It tells me the proportion of the total variance that's explained by each of the principal components. So I could boil those 20 individuals down to just one variable and still spread them out with half as much explained. I can explain half of all the variability in my data with just a single variable, 0.55. If I include the second principal component, I get an extra 10% explained for a total of 64%. If I keep going, I can explain 95% of my data with only 12 variables. And the last thing I was going to show you is this right here. Eigen S gives me eigenvalues and eigenvectors of a matrix S. So here are the eigenvalues, here are the eigenvectors, and this first column is the exact same thing that came out of PRComp. This is the first eigenvector of S. It's the exact same thing that came out of PRComp. So principal components is taking a covariance matrix. That's my total amount of information in my data. And then it's decomposing that into component pieces. And the pieces that it returns are just the eigenvectors of the covariance matrix. And then we can interpret these. We can say how much variance is explained by each of these. Suppose I can take 20 variables and I can explain 90% of the whole variance with just 3 of them. That would be pretty handy. I could look at those 3 variables and probably learn something structurally about the data. And then how do you actually learn something about the data? You could look at these numbers. The best way to spread my data out with one variable is to do this to them. Like in the Hall of Fame data, I said there were only 6 variables, and these numbers were all like 1/6, which means best way to boil the players down is to average their career stats. The second column was like positive numbers for slugging percentage and home runs, negative numbers for batting average and hits. Contrast power hitters with small ball hitters. That's the next best way to spread things out. Third component, there was actually an interesting story in the Hall of Fame data. Often you can take multivariate data, boil them down to just a handful of variables, still preserve most of the information that was in the total data set, and then by inspecting the numbers that make up those new variables, you can often learn something insightful about your data. I will show you several examples on real data sets. Next time we'll continue this story to see what these numbers tell us about the yeast data. There's interesting stories in the yeast data, like the technicians are different, the years are different, the strains are different, and we could look at that in different ways. We're going to do cluster analysis and see technicians grouped together. We're going to do principal component analysis and see the biggest contributor to differences in my data is technician and year differences, stuff like that. And then singular value decomposition, which I'll talk about next time, is very closely related to principal components. It has some extra features that it gives us that are handy with omics data. But right now, last time we were talking about differential expression analysis and testing, false discovery rates and stuff like that. That's inference. That's making formal decisions and statements and estimates with a stated level of confidence. This stuff is more exploratory in nature. We're making pictures, we're looking for outliers, we're looking for interesting, unexpected stories that we can learn about the data in a big picture way. All right, so I hope some of that stuck. We'll go through it some more and do principal component analysis on some real data sets. Best way to see what it's doing is to see it with examples. Here's an example. We did PCA. Look what we just learned. So we'll get practice with that. Questions? All right. I'll see you Wednesday.